Hey, AP Chem students, welcome back. We're moving on from ideal gas law to the kinetic molecular theory. The kinetic molecular theory actually is the basis for all of our gas laws, so you can actually derive all of the ideal gas law and thus the empirical gas laws from the kinetic molecular theory. There are four major postulates here. We're going to read through them. I left you a little bit of space in case you wanted to expand upon them, put some definitions or some other things down just out there. All right. So our postulates, our first postulate says that the size of the particle is very, very small. Negligible means small, very, very small. So we're talking about very small particles. And the other thing is we're saying that they're very, very far apart. So what we're saying is that if you think about a gas, those gas particles are very, very far apart, and so they don't actually have any attractions or repulsions to each other because of how far apart they are. The next one, the average kinetic energy of a particle is proportional to the temperature in kelvins. This is actually where we have our definition of temperature come in. Our definition of temperature is the average kinetic energy. So we're talking about how fast the particles are moving. As the particles move faster, we say the temperature goes up. As they slow down, we say the temperature goes down. All right. The next one, this is C. It kind of goes along with that first one being the attraction and repulsion part. We have the collision of one particle with another or with the walls of its container is completely elastic. That means there's no attraction, no repulsion, and it bounces off with as much energy as it had when it hit at the beginning. So there's no energy lost in friction or even the attraction or repulsion kind of keeping them together. So that's a big key there. The last one, all particles in a sample are in continuous random motion. The average kinetic energy of the particle is related to its average velocity. The other thing that we can take from this is right here. Our mass. Notice how our mass comes into play there. All right, in this formula. Sorry, we had a really fat letter there. All right, so we've got our mass comes into play here, and so thus it affects the velocity. So what we're going to say from this is that heavier molecules actually travel slower, and we'll actually revisit this in just a few minutes when we talk about effusion and diffusion, but that's where this comes from. All right, another big part of the kinetic molecular theory is right here, this Maxwell-Boltzmann distribution graphs. We have two separate graphs. So let's look at the first one here. This one right here. This is the same particle. This is the same substance here, just over different temperatures. So what we see is that at lower temperatures, we don't have that large of range of speed, if you will, right? And now think about what we're talking about when we talk about these speeds. We're talking about all the molecules in a sample. So some of the molecules might be coming right from just a collision, just finishing a collision, so their speed's not back up to normal yet, right? Or we might have some that have just got back up to speed or had a glancing blow, thus their speed's a little higher. All right. The big distribution here is what you should see is how as temperature increases, notice how our range grows. That's just a growing of 200 Kelvin, and then 600 and 1,000. We'll actually see a Maxwell-Boltzmann distribution graph a little bit later when we talk about kinetics, because they have to have enough energy to get over the hill. But what we're looking at, so you can see the key takeaway here is that when we have a higher peak, right, higher peak, kind of less area underneath it, we have a lower temp, right? Then as it spreads out a little more, look at this red one. Holy smokes. It goes from here all the way to there. Look at that range of speeds that we have. It is quite a bit there. Okay? Awesome. Now, if we look at it in terms of over here where we have different gases, and this is more relating to this formula up here. If we look, hydrogen is going to have a higher kind of range of speeds, and it's actually going to be moving. Its peak is maybe right in here somewhere. it's on average going to be moving faster because of our kinetic energy. If we look at this formula right up here, we see our kinetic energy equals half mv squared. So m is really small for hydrogen, so its average velocity of the particles is going to be a little bit higher than, like, say, oxygen, which its average velocity would be over here. Does that make sense? Now, a little bit of a confusing thing here, right? Kinetic energy is the measure of half times the mass times the velocity squared, right? Our temperature is related to that. So the average velocity of the particles is going to be different, but their average kinetic energy is going to be the same if they're at the same temperature. If we're at 298 K, their average kinetic energy is going to be the same, but their speed of their molecules or atoms is going to be a little bit different based on mass. All right? Okay, like I said, a little confusing, but hopefully we got that figured out. Now, a couple of things. We have effusion and diffusion. All right? Effusion is the ability or the speed. Maybe speed is probably a better word. All right? Speed at which a substance escapes from a pinhole. Like a pinhole leak, and we're talking about pinhole, all right? So we're talking about a pinhole leak. So, like, if we have a hole in, like, a helium balloon, how fast will the helium get out of there? And if you think about it, let's kind of look at this as, here's my container, right? But we have this very, very tiny hole right here, right? But the particle is bouncing all around, so how long does it take until it finally moves out through that hole, right? Because it's moving in random motion, right? It won't always get there right away. All right? And then we have diffusion, and this is just the rate that it spreads throughout a room, right? We're talking about spreading throughout a system. Okay? And both of these depend on the mass of the substance, all right? The heavier the substance, the slower it diffuses and effuses. Which makes sense if you think about it, especially in terms of our kinetic energy, our average kinetic energy. All right? Awesome. See you next time.